It's question show time. Your questions, my answers. As always, wherever you are, question pops in your brain, write it down, I'll gather them up, and I'll answer them here. But before I get into this week's show, I want to encourage all of you to go out and try to see Comet Neowise. This is the first bright comet that we've had in the Northern Hemisphere in decades. And we've seen it a couple of nights already. It's not great, but it's a comet you can see with your own eyes, and it looks really good actually in a pair of binoculars. So try to find a time. All you have to do is look to the north, and you should be able to see it in the evening in the Northern Hemisphere. If you're farther south, you're going to have to be a little trickier on when you go and look at it. But still, a comet. This is what we've been waiting for. Get out and see it. All right, let's get into the questions. Scott Rick, is it possible for two stars to circle one another so closely that they touch? Yeah, absolutely. The term for this in astronomy is called a contact binary. And this is when you've got two stars that are orbiting one another so closely that they sort of put out lobes towards each other and the stars are kind of connected. And it's not a very sustainable process. The stars are winding around each other. They are slowly getting closer and closer together, and eventually they will merge. And when they merge, that's called a red nova. And what you get is you get these two stars, smaller stars, maybe stars like the sun or red dwarfs or something like that, and they merge together into one larger star, and it sort of starts the process, their star formation, and you get a very bright flash when it happens. And in fact, astronomers know of a contact binary that is about to merge. They think it's going to merge within the next 5 years or so, although more research is still necessary for when and if this is actually going to happen. In 2017, astronomers reported that there was this star, KIC 9832227, and they had calculated how quickly the star was turning. And they calculated how quickly the stars, essentially the contact binary, was orbiting around itself, and they were able to measure how the speed was increasing as they were going faster and faster, as their conservation of angular momentum was speeding them up and up and up. And they had calculated that probably within the next 5 years or so, they would merge and create one of these red novae, and we would be able to see it in the sky, like right on time. But now there's been new calculations, and I don't think it's going to be that same time. But still, these stars are doomed to collide with one another. So yeah, absolutely. They're called contact binaries, and they are out there. Jason Sin. Hey Fraser, love the show. What is the maximum speed that a spacecraft could achieve by slingshotting around objects in our solar system? So theoretically speaking, there's no limit to how much of a speed boost you could get from slingshotting around an object. Practically speaking, there are limits, and a good kind of rough guideline is that you can use the escape velocity of the object to calculate about how much of a slingshot you could get in an optimal situation. So I'll give you a couple of examples here. Jupiter, the escape velocity from Jupiter out of the solar system is about 80 kilometers per second. And so if you did a really tight gravitational slingshot around Jupiter, you could get a speed boost of about 80 kilometers per second if everything worked out perfectly. Now, if you were coming into the solar system from some other star system and you wanted to get a gravitational slingshot from the sun, you could get a speed boost of about 650 kilometers per second, which is actually fast enough to be an escape out of the entire Milky Way, if you time things correctly. But practically speaking, you're dealing with the forces. You're going to get close to the sun, you're going to burn up your spacecraft, you're going to experience tremendous forces as you're getting cranked around the sun as you go around it. And of course, the greatest possible thing that you could use as a gravitational slingshot would be a black hole. And again, now you can get incredibly close to the black hole. And so you could go relativistic velocities, a significant portion of the speed of light. Of course, just imagine you're coming into a black hole, you're going around the black hole, and you're getting just totally cranked, and you're just going to get torn apart. So you have to balance all this. What is the maximum speed that you could go up to a black hole to get an increase in your velocity and still withstand the journey? And that's a calculation. Now, if you're going to try to do some sort of really complicated series of gravitational slingshots here in the solar system, it's just really important to remember that once you get to certain kinds of speeds, you're going to be escaping the solar system. And so let me give you an example, right? Like the escape velocity to get from the Earth is about, I think it's about 42 kilometers per second. And so if you go past the Earth and you get a speed boost that now takes you faster than 42 kilometers per second, you're now going to be on an escape velocity out of the solar system. And so you can't come back and get another slingshot around another planet. And so you would have to time things out correctly. But it's just sort of like as a rough guideline, you could go about 80 kilometers per second, which is still, would take you thousands of years to go to the nearest star system. But that's why these gravitational slingshots are so important. Ivica Pavic. How do astronomers and cosmologists map out and find their way around billions of stars inside billions of galaxies to be able to come back to specific ones and observe and study them? On your phone, you've got a latitude and longitude, which tells you your specific spot on planet Earth. That's a way that you can navigate yourself back to a specific spot. It has to do with the latitude and longitude. I'm going to get them backwards, but anyway, one of them is the sort of north-south on the planet and one is the east-west, and you can, any spot on the Earth has a very specific number. Now there's a version of that that is used for space, and so astronomers use this term called right ascension. And right ascension is essentially if you draw a line right through Greenwich, England, and then you mark 1 degree all the way around planet Earth, 360 degrees around planet Earth, each one of those is going to be a 1 unit of your right ascension. And so astronomers know where, imagine if there's this line that comes out of England, out into the universe, then of course England is turning, the world is turning, and so that point is constantly moving over the course of an entire solar day, sidereal day. So that's the one thing, and so you can measure to the west or to the east of wherever that imaginary line that passes through Greenwich, England is. And then the other thing that astronomers use is a term called declination. This is the altitude above the equator. So again, imagine you've got the Earth. The Earth has the equator, this invisible line that goes out into the universe, like a ring around the center of the Earth. And you can measure above that line. If the equator is 0 and the pole is 90 degrees, then you can break that up. And so if you use the right ascension number, which tells you just how far ahead or behind England that part of the sky is, and then you can use the declination, which tells you above, how high above or below you are from the celestial equator, then you can find any spot in the sky forever. And so all telescopes have this system mapped inside of it. And so if I say I want to go to a very specific location, I can either punch in the right ascension and declination numbers, and the telescope will turn to that exact spot in the sky, or the telescope has a database built inside, and I can say, I want to see Mars, and the telescope knows the right ascension and declination numbers for Mars, and it points to Mars. And so astronomers have a very elegant system for mapping out the location of anything in the entire universe. Sam Hill. Fraser, question for you. Is it possible for a solar system to have a planet that orbits backwards compared to the other planets in that solar system? Thank you. Theoretically possible to have a planet that's orbiting backwards from the rest of the planets, but in order for you to actually be able to have that, something weird had to happen. When we look at the solar system, when we look at the solar system from above, we imagine all of those planets turning counterclockwise. All of them. Venus, Mercury, Jupiter, Uranus, even Pluto, they're all turning in the same way, and they're all actually, in many cases, they're orbiting in the same direction, and they're actually all mostly turning in the same direction, except for Uranus and Venus, which tells us something weird happened to them. And so that tells you that the formation of all the planets is kind of connected, that they all formed as this one big gas cloud early on, and the planets started to form their own rings out of the gas cloud, the protoplanetary disk, and then they carved out their area and they continue to orbit to this day. And so to have a planet that is going in the exact opposite direction, something had to happen. Now, one possibility is that you had some really bizarre combination of three-body interactions. So the planet got too close to Jupiter and it got kicked out on some weird orbit, and then later on another orbit it got close to Saturn, and that somehow made its orbit turn backwards, and then something else sort of more circularized it, and now it's going in the opposite direction from the rest of the planets. But the other possibility is that you get a capture. So there's some kind of rogue planet that's just floating through the Milky Way, and it gets too close to the solar system, goes into a three-body interaction with Jupiter or Saturn or the Sun or whatever, and ends up caught in orbit around the solar system. And then it would just be going on whatever orbit it started out as. But you're not going to get a nice circular orbit. You're going to get something weird, something highly elliptical, something that's highly inclined to the rest of the planets in the solar system, something that tells us that it clearly came from some other location. So we do see a couple of objects. Neptune's moon Triton is orbiting backwards from the rest of pretty much of all of the large moons in the solar system. And again, astronomers think it's a captured Kuiper Belt object, and it just was at the wrong place at the wrong time, and it got turned into a moon of Neptune. But it's not a very common thing that we see. Wilhelmo de Occidento. How are you going to get nations to agree on putting up a fleet of super devastating space lasers into orbit? So this question is related to the idea of the Breakthrough Starshot spacecraft, where you have this incredibly powerful laser, something that's more powerful than any laser that's ever been built to date, that fires a quick blast at a spacecraft and accelerates it to very high velocities to be able to make the journey between star systems. And you have a very powerful laser that's in orbit around the Earth, and it's, zapping spacecraft off to Alpha Centauri, but that laser could be turned around and could be shot at locations on planet Earth and could do a lot of damage. It could also be used to blast apart satellites that are in orbit. And so you can imagine there would be a certain amount of nervousness by the nations to allow something that could be there. And maybe they could get to a point where they can agree with each other and they feel like they trust each other to have this incredible petawatt, exawatt laser orbiting the Earth. Maybe there's some places they could put it that it could do less damage. And so one example maybe is on the far side of the moon. Put it out beyond out at the L2 Lagrange point, and if you aim it perfectly, then it's going to have to shoot through the moon to be able to hit the Earth. Although the L2 isn't perfectly on the other side of the moon. You can also put it farther away, like maybe have it out at, say, the Earth Sun L2 Lagrange point, where it would have to, wouldn't have the power to do any damage back on Earth. And then another idea that I've heard is you put it on the other side of the Sun, at the L3 Sun Earth Lagrange point. And again, it's a fairly stable point, and it can't do any damage because it can never see the Earth. So you've got a couple of places you can put it, but it will be interesting to see the negotiations as these powerful lasers get put into orbit for very useful, peaceful purposes like deorbiting space junk or accelerating spacecraft. But they can have some downsides as well. But I mean, this is technology. We deal with this all the time, right? Some technology can be used for good and evil. J2 I wonder what would happen if Superman could reverse time on a black hole to the point that it was no longer spinning. Would it collapse into a giant explosion, spewing out whatever matter and energy it had consumed, or would it just fade away? Interesting. You wouldn't have to reverse time to stop a black hole from spinning. All you'd have to do is drop material into the black hole in the opposite direction that the black hole is spinning, and each piece of new debris that goes into the black hole would slow down its rotation a little bit. And if you had enough material, you could eventually just perfectly stop the black hole from rotating. Now, it wouldn't disappear, it wouldn't explode, it would just sit there, ready for a meal. Feed me. And in fact, so one of the really cool ideas of a way to generate power is this idea of the Penrose process. And what you do is you've got this rapidly spinning black hole, you drop material into the black hole, and as it just is about to drop into the black hole, it tears apart, part goes into the black hole, and part, now that it has less mass, gets spun out really fast, and then you capture that mass, absorb the kinetic energy, and you use that to power your advanced civilization. And it's probably one of the most efficient ways that you could use energy in the entire universe. I think it's like 39% of the energy, the sort of theoretical limit of energy. The problem is the more that you do this, the more you're slowing down your black hole, and eventually your black hole will stop. And you're going to have to feed it a bunch to speed it up again. until it's rotating, and then you can bleed off that energy again. So imagine a black hole as like a giant battery that you can speed up and speed down, like a big flywheel that you can extract energy from when you need it. Black holes are going to be incredibly useful for really advanced civilizations, for all kinds of things. So we should be, we should be very careful. We don't want to use up all of our black holes. Forward synthesis. If a warp drive has you experience 0 time during the journey, no matter the distance, then how do you control when and where you stop? That's a great question. Now, let's just start with just the acknowledgement that a warp drive is a purely theoretical thing that Alcubierre did some math, I think back in the 1980s, and said, well, maybe it's possible if you're able to come up with something called negative mass, then you could maybe have a warp drive. But as I mentioned in a previous video, even if a warp drive is possible, it's not going to work the way Star Trek and Star Wars and science fiction has led us to believe. They're trying to tell a story. They're trying to say, wouldn't it be cool if we could fly from world to world in our spaceships, and if we did, it would feel like you were sailing on the oceans, and you would just like hop in your spaceship and you'd be in one location, and then you'd tell your first officer that they've got the helm, and then you would just spend time making the journey just the way boats do. Well, space isn't the ocean, and spaceships aren't like boats. And warp drives are not like propellers. This analogy is going a little too far. And so one of the understandings is that when you actually turn on your warp drive, one, we can't figure out a way that you could actually turn on a warp drive. And then the other problem is we can't think of a way that you would turn off your warp drive. So that's a problem. And so, in answer to your question, the answer is, we don't know. If you can turn on a warp drive and you're inside the warp bubble, there's probably no way to turn off the warp drive again. And then the other problem is that essentially the tidal forces inside this warp bubble that you're creating are incredible. And so if you're at the middle of this warp bubble, you're going to get destroyed. It's going to be like you're really close to a really heavy mass. And so you're going to need to generate a very large warp bubble and then exist right out at the very edges of this warp bubble where you're experiencing the least amount of tidal forces on your starship. And so there's no way to turn them on. You travel instantaneously. There's no way to turn them off. And even if you are able to make them go, you're inside the warp bubble that's going to try to destroy your ship. And again, it's all just completely theoretical. It's highly likely that we will never figure out the technology. And I know that science fiction has told us to expect it. And I'm sorry. DHR 18. If Planet 9 exists, would it likely be a planet that formed with the solar system or a captured rogue planet? And if it is a local planet, did it likely form that far out, or had its orbit shifted by maybe an encounter with another star early in the solar system's life? Could it be in an orbit outside of the plane of the ecliptic, making it that much harder to find? We talked a bit about this idea of a captured rogue planet earlier on in the episode, and so that could be one possibility, although it's fairly unlikely to be able to capture a planet of that kind of a mass. So the most likely explanation is that it formed within the solar system like the rest of the planets. It's a Kuiper Belt object, but maybe with the mass of Uranus or Neptune. It's very large. And like the rest of the planets, it probably formed a little closer into the sun in the beginning, and then the planets all migrated out a little bit, and so it probably did that as well. If it did go through some kind of severe interactions with the other planets, with maybe Neptune and Uranus, then it could very well be on a highly inclined path compared to the rest of the planets, like Pluto is. And that would absolutely explain why astronomers haven't been able to find it. Astronomers have scanned the plane of the ecliptic. This is the plane that passes directly through the sun, and most of the planets are on this, almost exactly on this plane of the ecliptic. They'll be a little above, a little below, but in general, that's where all the planets are. And when you actually look up in the sky and you can see, oh, there's Jupiter, there's Saturn, there's Mars, they're all lined up. They all path in the exact same direction across the sky. And so you would expect if there are more planets, they would be along that plane of the ecliptic as well. And astronomers have looked very carefully in that region, and they've pushed modern telescopes to their very limits to what's possible to see. And so far, they haven't been able to turn up anything other than dozens of very large Kuiper Belt objects. So we're going to need a more powerful telescope something like the extremely large telescope or the 30-meter telescope or something like that that's going to be capable of imaging to a greater depth to see objects that are fainter inside the plane of the ecliptic, or we're going to need something that is scanning the entire sky to find things that are way outside of the plane of the ecliptic, and they are a lot brighter, but it's just that no one thought to look in that specific location. And I know this seems really surprising, like, how could astronomers not think to look above and below the plane of the ecliptic? It's just that space is enormous, and the telescopes, often their resolution is so small that they're able to image, like, a hair held, I don't know, a kilometer away. I forget the exact numbers. Maybe Chad will put an example here. And so imagine you're trying to just examine the sky bit by bit. And of course, to find a planet, you need something that changes from night to night. So not only do you have to scan a region night after night, to just map out what's there, but then you have to come back around and map it out again to see if anything's moved. And it's just a laborious process. And fortunately, we're going to have this incredible tool in the next couple of years called the Vera Rubin Observatory, previously the Large Synoptic Survey Telescope. And it is going to be imaging the entire sky every couple of nights at that level of depth that's required to be able to find objects like Planet 9 and tons of asteroids and supernovas going off and comets before anybody else. I cannot wait for that telescope to come online. That's going to be the one that finds Planet 9. That's going to be the one that maps out all of the dangerous asteroids in the solar system. That is the most important telescope that's coming online. If I had to choose between Vera Rubin and James Webb, I would take Vera Rubin. That's how important this telescope is. And we're only about a year and a half away from it showing up. So stay tuned. I'm going to do so many videos about the Vera Rubin Observatory. SPAC. I think this is proof that we are missing a lot of info, something like a whole other plane of existence unaccounted for. And it's very good news. It potentially means current laws are just a construct based on our limited understanding. FTL will be a thing. Black holes are just batteries. Time is just another road, etc. So this is a question relating back to this discovery of using masars as a way to calculate distance in the universe and just how the cosmology crisis. It's definitely exciting to see what was a mainstay of physics start to, people to realize that there is some fundamental disagreements in how this works, and it opens up an opportunity for a lot of new theories to come forward to try to modify it. But also, when you think about, say, Einstein's general theory of relativity as an improvement over Newton, all of Newton's math still holds. You can still use Newtonian physics to predict the movements of objects in the solar system, to predict the movements of spacecraft with incredible precision. It's just that Einstein's version does a better job in places that are very extreme, when you're in intense gravity wells, when you're moving at enormous speeds. That's where Newtonian mechanics falls down and Einstein's math holds up. And so now you're finding a place where maybe, Newtonian is starting to not able to make the predictions. Maybe Einstein's relativity is unable to make the predictions. So you're going to need some other theories to be even more accurate, right at the very edge cases of everything that you're looking at. And so it's not going to be like, oh, it turns out Einstein was completely wrong. There's no such thing as time dilation. There's no such thing as acceleration and free fall, etc. All these things. And in fact, it turns out that Newton was wrong. It's not going to work like that. It's going to be like, now we've filled in all these missing pieces, and here's this other theory that both explains everything that Newton saw, explains everything that Einstein saw, but also explains all of these additional issues. And whenever anybody tells you, well, Einstein's wrong, I've got this idea for the theory of the universe, they've got to be able to go through that process and explain each one of all of the observations that have been made so far, and then make testable predictions for other things that so far science has had a hard time figuring out. And so it doesn't necessarily mean that FTL will be a thing, that black holes are going to be batteries, although I did mention the black holes are batteries early in the episode. But we don't know which of our understandings of the physics are completely wrong and which ones are almost 99.999% right. And it's just a matter of continuing the process of just trying to understand the universe, working harder, digging deeper, continuing to do experiments, continuing to develop theories, build larger telescopes, larger particle accelerators to try to just continue to progress our knowledge. And we don't know. I mean, that's the great thing about science. And I mentioned that in the last episode, that it is a mystery that we don't know the ending to. And that's the part that's so exciting for me, is that we get to be along for this journey as the mysteries are discovered, as the answers are uncovered. And then, of course, each answer creates new mysteries, and the process continues forever. Dizzy Azzy. Are those huge stars that leave no remnant behind more common than stars that leave a neutron star or black hole? It seems that with how old the Milky Way is that they should be common, but they're rare. How can that be? So the kind of star that we're talking about, the one that doesn't produce a supernova, just goes from star to black hole, it's believed that those only happen with the most massive kinds of stars, the stars that are hundreds of times the mass of the sun. And so those are not super common in the Milky Way, they're not super common in the universe. And in a recent survey, I think I mentioned this in the episode, that maybe about 10% of the stars could be going through this process, this unnova process, where they just collapse into a black hole and they never get the supernova. That's today. With the kinds of star formation that's going on in the universe today, the kinds of nebulae that are collecting together and producing stars. But if you go all the way back to the beginning of the universe, before there was any heavier elements, there was just this primordial hydrogen and helium, and they were potentially forming stars that were hundreds of times the mass of the sun, maybe thousands of times the mass of the sun, maybe tens of thousands of times the mass of the sun. Astronomers are still trying to figure this out, and it's a very important question. And so what is a very rare event today might have been just the way all of the stars acted at the very beginning of the universe. These they're called the population 3 stars. And this is a time that astronomers are really excited to be able to eventually be able to see. The James Webb can't do it. Some of the biggest telescopes on Earth aren't going to be able to do it. There are a few experiments that might give some sign of these first stars, but it's going to take much bigger telescopes like LUVOIR or the Origin Space Telescope, or even bigger telescopes than that, to actually allow us to see so far into the universe that we're seeing those first stars form shortly after the Big Bang. And it is one of astronomy's greatest desires to be able to do that. DAX99. Why do scientists assume that planets orbiting red dwarf stars are likely to be tidally locked rather than a synchronous orbit like Mercury? Is there something special about Mercury that I'm not aware of? The difference here really just comes down to the distance of the planets from their star. So we'll give you an example of a red dwarf star with some planets orbiting around it. You've got the TRAPPIST-1 system. TRAPPIST-1b, which is the closest world in to TRAPPIST-1, is orbiting at 0.01 astronomical units. And that's equivalent, I think, like 1.7 million kilometers away from TRAPPIST-1. Compare that to Mercury, which is orbiting at 58 million kilometers from the sun. And then when you compare that, say, to the distance that the moon is orbiting from the Earth, the moon is orbiting at like 280,000 kilometers from the Earth. And so the moon is actually relatively close, closer than the TRAPPIST-1b orbits around the red dwarf star. The large moons around Jupiter orbit relatively close. So you're only going to get this tidal locking when the planet or the moon is orbiting very close. We're very excited about planets in the habitable zone of red dwarf stars, because it's nice to have an Earth-sized world orbiting within a habitable zone of anything, but the habitable zone around a red dwarf star is very small, and so you're going to end up with planets that are very close in to the star. And that's when you get that tidal locking, where the interaction of gravity between the planet and the star stops the planet's rotation relative to the star, and it only shows one face all the time. Streak 1. Here's a question. How do they decide when to launch a mission? They could launch something now to do research sooner, or launch later to use new technology to get more information. I think it would be an especially hard question for a new term mission like New Horizons, or even sending a mission to explore Proxima Centauri or something. Funding is probably part of it, but how do they decide when to put the funding into further development or to building the probe and launching it? So When a space agency like NASA or JAXA or ESA goes through the process of developing a new mission, they have their science goals, and these are provided by the science community. We want to know where those first stars in the universe looked like. We want to know what's on the surface of Pluto. We want to go back to Neptune and explore its moon. So these are the science goals that the scientists provide, and they provide that to the space agency through this process called the decadal survey. And we've talked about this a bit in the past. I'm sure when the new decadal survey is complete, we'll do a whole video on this. Every 10 years, the science community comes together and they provide their wish list of what they want to do. And then from the space agency, they sit down and they look at the budget that they have available to them and they compare that to the science goals that have been provided. And then they have different classes of missions. So they have these, and this specifically with NASA, they have the smaller class missions. I think they're called the Discovery class missions, and they're a few $100 million. They're a fairly simple spacecraft built on a fairly known architecture, designed to answer a couple of very simple questions. You've got things like a mission to an asteroid, or you've got the InSight lander is an example of one of these missions. And then NASA also has the flagship missions, things that are potentially billions of dollars, which are going to last for a long time. They're going to do a lot more science, things like, say, Curiosity or James Webb or Hubble, Cassini, things like that. And when they're developing a new mission, they purposefully bring in new technology and new techniques, and they try to sort of push the envelope of what they've already done before, this idea of technical uncertainty. And so they will identify in their proposal what are some of the big pieces of technical uncertainty. What are all the stuff that we know how to do, and what are the stuff that we're going to have to develop a new method? And so James Webb is a great example. There's a whole bunch of different pieces of technical uncertainty that were part of the James Webb Space Telescope. This folding sun shield, the folding part, the size of a mirror, a segmented mirror. There was like just a bunch of different technologies. Each one had never been tried before. And the space agencies know that the more of those that you put into this process, the more expensive, the more likely you are to go over budget, the more dangerous it is to try to launch this mission. And so they try to pick this sweet spot. What is the most science that we can get for the budget that we have, and have the littlest amount of technical uncertainty, but also push the boundaries a little bit to make sure that we've solved some problems for future missions. And they sort of boil that down, and they put in a lot of work and a lot of documents and a lot of meetings, and then they come up with a plan for what that mission is going to be. And then it changes over time as things end up being easier and more complicated than they thought. And then next time around, a new mission comes up. Some of the discoveries, some of the techniques that were used on the first mission are reused on the next mission, and that lowers the budget for the next mission. And so we're not in this world like, say, with cars or computers where they mass produce them. Each one is still an individual bespoke robot, but they still try to, go through this process very carefully, try to save money where they can, and try to get the most science they can for the littlest budget. I highly recommend, a lot of these design documents are fairly easy to read, and you can go back and read the design documents for pretty much any spacecraft that you're familiar with. Just Google it, and they're very fascinating. So I highly recommend that you take a look at it. All right, those are the questions. I hope you all enjoyed this show. As always, wherever you are, question pops in your brain, write it down. I'll gather them up. I'll answer them here. And remember, go see Neowise. Go see a comet with your own eyes. All right, we'll see you next week.